Hello everyone, I hope you're having a great day. And in this video, we'll be looking at the MySQL Client Server protocol. So this is the raw bits and bytes that actually travel over the wire, whether over the network or via your loopback address when you're actually performing some communication with your MySQL server, whether that's from your application or from your command prompt window. So a little bit of a preface into this video. I'll be primarily focusing or going through the MySQL documentation that's available. I'll link this below as well. Along with that, I have a couple good nifty resources. So one of them is the O'Reilly excerpt from the book. I think it's called MySQL Internals. Yeah, MySQL Internals. So chapter 4. It's actually available for free on the O'Reilly website. And this is a very summarized and all in one place kind of a documentation for the whole protocol. Let me bring this back into line actually. Yeah, great. So this is a very handy page to have because it essentially summarizes the entire protocol in a single web page. So it's very useful in that regard. Along with that, there's a talk on FOSDEM by Daniel Van Eden, and he discusses a little more in depth regarding the authentication protocols, how the security works, how the compression works, and all of that. So that's something I would suggest you check out. In this particular video, we'll be focusing on the packing logic of the protocol instead of the states of the protocol, although we will be going over the states as well. Anywho, apart from that, the reason I got into this protocol was because I was working on a Rust application. Now, this is not complete by any means. It was more of a project for me to learn Rust. And that's how I got into learning about the MySQL protocol. And I think it's a good protocol to know regardless because it helps you understand how things work under the hood. And even if you do not use MySQL, perhaps if you're using some other data sources like Mongo or even your raw HTTP connections, have some sort of raw bit packing logic, byte packing logic, and it helps to understand how various protocols can accommodate different data types, how you can efficiently package your layer 7 packets and all of that. So a little bit about the setup I have for this lesson. I've got a normal Docker container running MySQL. This is the MySQL image that you get off of Docker. I've got the root password as ASD. This is in no means going to be on production or on the web. It's just a local server. So I think it helps illustrating with a simple password. Along with that, I've got my server. I've got my application running, which I've been working on. So the primary objective of this application for now, or at least the reason I'm using this in this particular lesson, is because it unpacks the layer 7 packets that MySQL sends, the communication that happens between the client and the server, and it just prints it out for us to read easily. You can get by with something like Wireshark if you just sniff at all of the packages and sniff at all of the packets, and that's also fine completely. It's all up to you. So the first thing that we're going to consider is the actual process through which the connection goes through. Let's say we've got a client and a server. So on the left, we've got the client, and on the right, we've got the server. The client is going to initiate this connection by creating a connection on, say, port 3306. That's the default MySQL port, and the server acknowledges that connection. As soon as that connection is created, now let me just add to the fact that this is TCP. As soon as that connection is created, the server sends a handshake packet. And the handshake packet is going to include details like the kind of version, the kind of MySQL version the server is running, and some of the features that the server supports and things like that. So for example, one of the fields in the handshake packet represents whether the server supports SSL. If the server does support SSL, the client is going to come up to a decision. So if the client is also enabled to create an SSL connection and the server supports SSL, it's going to send an SSL request. It's going to send an SSL request. We're going to look at the details of all of this very shortly, and it will create a TLS connection. So you have the encrypted client hello and the TLS negotiation that goes on between the client and the server. And finally, the client is going to send the handshake response. Handshake response. If either the client or the server do not support SSL, this entire block is going to get skipped, because then you don't need to perform an SSL connection and it will just skip all of this. Once the handshake response is received, it's up to the server. So for cases like for a simple MySQL password, it's not really a problem for if you're using MySQL native password. However, there are certain authentication methods like the caching SHA-2 password, or the or if you have a multi-factor authentication switched on for your server, it's going to need more data than what is available in the handshake response. So the handshake response contains an encrypted version of your password, and the server verifies that. However, the server might request more data. The server could request you to switch the authentication method as well. So in that case, you'll get an auth switch request. And then depending on that, you would respond with an auth switch response. Let me just write response here. Once you have that, all of that, it can go through multiple factors. So if you have two-factor authentication, it's going to request two-factor data and all of that. And then finally, once all of the back and forth is completed, you'll either get an OK packet or you'll get an error packet. So this determines whether your connection was successful. If you got an OK packet, it means your connection was successful. If you get an error packet, it means your connection was not successful, and it has failed. You'll probably have to retry. Now, this failure can happen due to a wide variety of reasons. One of them could be that your password is incorrect. Another one could be that your client is way too far behind in the version and it does not support the authentication method that the server requires you to use. So all of those cases can cause a failure in the authentication. Anyways, so let's move forward. We'll go through the documentation together. We'll take a look at the connection lifecycle. And then after that, we'll go into the protocol basics and understand the packet structure and everything. So once the client connects, your state goes into authentication. After a successful authentication, if you have an unsuccessful authentication, then it goes into an error state and then the client disconnects. Otherwise, if you're in the command state, that is when you actually are able to perform commands on the MySQL server. Let's take a quick look into the connection phase. So this is the connection phases. These are the connection phases that I was describing. You've got the initial handshake packet that this comes in from the server. Then the SSL exchange might happen if both the server and the client support it. The client is going to respond to the initial handshake packet with the authentication method or with the authentication details. At which point the server can suggest that the client switch its authentication method. If the client does not support that authentication method, it's going to disconnect. However, if it does support it, you're going to have that back and forth of the authentication method continuation. And then finally, once the connection is successful, you get an OK packet. Now let's take a look at what these packets are. I will start with MySQL packets. So each and every packet of a MySQL connection has a header of 4 bytes as a header, and it has the remaining payload of the packet. So let's take a quick screenshot of this video, this page, and let's bring it over here. I'll get rid of all of the data that's there from earlier. Paste this image. It'll be easier to illustrate over here. All right. So in all of the scenarios, you're going to get a packet with the first 3 bytes being the length of the payload. the fourth byte will represent the sequence ID. So for example, when the handshake starts at the beginning, you'll have the sequence ID of 1. Then when you respond with the handshake response, you'll send the sequence ID of 2. So that's the packet number that's been exchanged. And that is in order to maintain sequence, like maintain in order delivery of packets in the entire communication over the course of the connection. And if at any point you get out of order packets, whether that's on the server or on the client, either of those will immediately terminate the connection because something has gone very wrong. Finally, it does say a string where, but let's ignore that for now. It's a payload of that's the actual payload that contains all of the data for the packet. Okay, so one thing to note about the header is the size is a 3-digit integer, 3-byte integer. However, it is a integer with the least significant bit first. So since this is for example, in the illustrated example, this is a 1-byte packet. And as you can see, the header has 010000 for the size, the first 3 bytes. And then finally, the last byte represents the sequence ID, which is 0. And this is the payload, which is 01. And as you can see, it starts with 01. And eventually, once this becomes, let's say the packet size keeps growing, this goes to FF. And at that point, this one will become 01 and 00 and so on and so forth. So all of the integer types that are in MySQL will be represented as least significant byte first integers. I believe it's called Little Endian, but I'm not sure, so don't quote me on that. And this is independent of your platform. So your platform might be Big Endian or Little Endian, but this format of the payload of the order of the bytes will not be dependent on your platform. A quick aside, if you've got packets larger than 16 megabytes, normally this does not happen unless you've got blobs stored on your database, which again, if you have, then it might be something worth thinking about a little longer, because you probably should not be hosting blobs in your MySQL database. So anywho, if you do have it, then if your packet size is larger than 16 megabytes, because that's what FF would represent. If it's larger than 16 megabytes, you're going to keep getting packets with FF until the remaining data is under the 16 megabyte limit, at which point you'll get a normal payload ID. I mean, normal packet size. Now, one more thing to consider is the fact that when you perform any sort of connection, whether that's based on sockets using whichever language you're using, whether that's Python or you're using C or anything, you're going to get a buffer. You can set the size of the buffer to 4096 bytes. Ideally, it's suggested to keep it at 4096 bytes or 4 kilobytes. The buffer is going to fill up with all of the TCP data. The TCP data comes in multiple TCP packets. Each TCP packet on average, well, I wouldn't say on average, but normally in a normal configuration, unless you've got jumbo frame switched on in your network, normally each of your TCP packets is going to be 1500 bytes. The problem comes up here is the problem that comes up here is what kind of abstraction does MySQL offer us? So this is the TCP layer is layer 4 and MySQL packets are operating on layer 7. So in one TCP packet, there may be multiple MySQL packets, or there will almost definitely be multiple MySQL packets. So let's say this is a MySQL packet, the 2 lines, and that's the data in between. So there may be multiple MySQL layer 7 packets within a TCP packet. On top of that, towards the end, there might be certain packets that, oh, sorry, I think this is still outside the view a little bit. Let's see, does that make it better? Let me zoom it out a little bit. I think that's better. Right, that's much better. So your last MySQL packet might be split into two, or split over two TCP packets. So a part of it might be in one TCP data frame, and the other one will be in the other TCP data frame. So if you're implementing something like a event loop, or you're constantly polling a buffer, so you have to take into account the fact that you might not have received the entire MySQL packet. It might be split across multiple, either whether that's multiple TCP packets or whether that's multiple polls of the buffer for the socket that you have received from the operating system. Anyways, let's proceed with some of the data types. The primary data type for numeric representation is the integer. Let's take a quick screenshot of this and bring it back to our whiteboard. Beautiful. So the primary data type for any numeric representation is an integer, and there are several types of integers that are used in the MySQL protocol. So primarily, you're going to be seeing integers of size 1, 2, 3, 4, 6, and 8. These can vary depending on the use case. So for example, I've not come across a use case where I needed to parse an integer with 6 bytes of data. I have come across all of the other situations, although I'm pretty sure this might exist somewhere in the protocol. It's just that of the parts that I've implemented, I've not seen this. Arguably, the more important part of this page is the length encoded integer, because this thing is going to come up very often. It's going to come up almost everywhere, especially in terms of when we're parsing strings. This is going to come all over the place. So let's take a look at what this really means. One of the challenges with a fixed length integer is, well, it's fixed. So let's say you've got an ID field, right, in your column, and that ID field can vary from being a 1 byte integer to from being something that's, for example, under 255 numerically. So that can be represented using just 1 byte of data, compared to the same integer field might even be closer to 4 million or 3 million. So in that case, you're going to need a 32-bit integer or a 4-byte integer to actually represent such a field, right? Now, it would be very inefficient if we will be using the same 32 bits for the integer that can be under 1 byte, as well as 32 bits for the integer that is 32 bits, right? So in order to overcome that, what MySQL does is, whenever there's if a field is encoded using the length encoding, or if it's a length encoded integer, when you look at the first byte, you're going to look at the first byte, and if this byte is below 251, then that's it. That's your number. That's your number. The next field over, the next byte over is the next field. It's the next field of your data frame. However, if your number is OXFC, which is 251, in that case, to get the number that you're after, you're going to have to look at the next two fields. So these next two fields are going to represent the numeric value of your actual number. Similarly, you've got OXFD and OXFE. So in the case of FD, you're going to look at the next 3 bytes. In the case of OXFD, you're going to look at the next 8 bytes. So in total, OXFE is going to take 9 bytes of storage, or 9 bytes on the wire, whereas OXFD will take 4 bytes. So this is 4 bytes, this is 3 bytes, 3, and this is 2. This is a single byte. Why do you need such complicated processing? Well, you see, we're so used to getting JSON, or so used to getting serialized data, that we have to think about it on the network level. On the network level, it's just bits, right? And you have to know some sort of way. So if you've got like a a huge dump of hexadecimal numbers, you have to know where one field starts and the next one field ends and the next field begins. So you could be having, let's say you've got 8 bits representing the ID, and then you might have a string that represents that has the name of the user that's logged in, for example. You have to know that this ID is 8 bits to know how to process the user's name. If you are not aware of this, you won't be able to process the user's name, because what if it's a 2-byte integer? You might end up parsing this much data into your integer, and then your name is going to be cut off halfway through and your integer value is going to be incorrect. So that is the main reason for all of this, all of the strict sizing guidelines for the communication protocol. Now that we're done with integers, let's take a look at strings. So right here in the connection, in the protocol basics section, in the basics data type, let's take a look at the strings. So strings are pretty straightforward, but I'll take a screenshot of this anyways and bring it into my whiteboard. Awesome. So the kinds of strings that we'll be dealing with on a regular, when we're processing MySQL command packets or MySQL packets in general, some of them are going to be a fixed length string. So you know from the specification or the documentation itself that this string is going to be 8 bytes long, or things like that. In other situations, you will be getting a null terminated string. So the string can be any length. You just have to keep going until you come to a byte that represents 00 in hexadecimal. And that's when you know that you've reached the end of that string. Then you've got a variable length string and a length encoded string. Both of these are very similar. So a variable length string, let's say you're parsing a packet. In some field of the packet, you're going to be told that a future string is 8 bytes long. And then when you get to that field, you have to take the next 8 bytes to actually process the string. As for the length encoded string, in the case of a length encoded string, you've got a length encoded integer followed by a string of how much ever this is worth. So let's say this integer represents n bytes, and that's how many bytes are going to be in this string. Now the length encoded integer is the one we read about in the previous page, where you've got either 1 byte, you've got 3, 4, or 9 bytes to represent the total size of the integer. Finally, we've got the rest of packet string. The rest of packet string basically means that read all of the data till the end of the current packet that we're parsing, and that's your string. So this string ends at the end of the packet. So now let's take a look at all of the steps that the connection goes through, like we were talking about the handshake. I'll open up the handshake documentation here. SQL packets, let's go into connection phase, handshake. So like the documentation says, and like I had explained earlier, you've got a plain handshake, in which case the server sends a handshake packet and then you respond with a handshake response. Otherwise, you're going to get a server sends the handshake packet. You respond as a client, you respond with an SSL request. Then you move over to an SSL connection. So since MySQL actually performs plain text as well as SSL on the same port, it needs to have this sort of communication so that both of them are ready to switch over to an SSL connection. Then finally, once the connection is secured with SSL, you're going to go over and switch over the handshake response. So let's take a look at how all of this works. In the handshake packets documentation, we've got certain details. So it says that at the beginning, you're going to have a single byte that is always 10. You're going to have a server version that's a human readable string, and that's null terminated. Anyway, let's go over all of this real quickly, but with an example. So I've got my server running. Beautiful. I've got my server running here. I've got my man in the middle proxy running here so that I can intercept all of the communication that happens between the client and the server. And finally, let's go into the MySQL command line. So I'm going to do MySQL u root pasd. My host is the loopback address. My port is 6033. That's the port my application is running on, the Rust application that I was working on. And yeah, I think we have all of the data that we need to perform the login. So there we go. Very mundane login, doesn't seem out of the ordinary. Let's take a look at the logs that have come in. So as soon as the connection is created, we start listening from the server and the server sends us this packet. Let's take a look at this packet along with the documentation that is mentioned. I'm going to take a screenshot of this. And let's bring this over to, you know what, let's take a screenshot of this first. Get rid of these pages. And the old screenshot as well. Great. So we've got this screenshot right here. We'll increase the size a little bit so that we can read. Beautiful. So let's take a look at all of this one by one. As we had read in the earlier slides, that the first 4 bytes of the packet hold the header. This is the header of the packet. So from byte 0 to byte 3 is the header. The first 3 bytes are the size of the packet, which is 74. So if I was to start counting from here all the way to the end over here, I would be able to count 74 bytes. Now do note that on the wire, on the TCP or in the buffer, there will be other data following this. This is the, like, right after this, I'm going to have the next packet's data, since it's all in just one long stream of data. What this application has done is it has, depending on the size of the header, it has actually stopped processing this at this particular byte, because that's the end of the packet as it was described in the header. And right after this, we'll have the data, we'll have the header for the next packet. Anyways, so the sequence number here is 0, as we expected, because this is the first step in the connection. And right after the sequence number, we've got OA or 0A that represents always 10. This value, so 10 is in hexadecimal. It comes out to OA. Right after that, we've got a server version string. So this is a human readable string. This is a human readable string and it's encoded in UTF-8. So 38 represents the digit 8 in UTF-8. I'm running MySQL 8.0.32, so that's what it represents over here. So 38 is 8. 2E is for the decimal point right here. Then you've got the 0. You've got the decimal again. You've got 32 right after that. And then finally, we've got this null termination, which hints to us that, you know what, this string is terminating right here. Right after that, we've got the 4-bit integer. This 4-bit integer represents the thread ID. So there's the thread ID over here is 9, since the least significant digit is right here. Least significant byte is right here. So looking at this, what really is the purpose of the thread ID? Well, MySQL connections are sequential. They don't have an event loop or anything like that. So it's always going to be a request response model. The client requests something and the server responds with it in the client request. There's no asynchronous communication, nothing of that sort. So a thread ID keeps track of all of the details of the thread, what state the thread is in, especially in the case of if you're developing something like proxy SQL, where you are multi-threading multiple clients onto one connection. All of those things will eventually lead to you having to track your threads, and the thread ID is very useful. Right after that, we've got the auth plugin data. So the auth plugin data is essentially it's like a salt that you have to use for encrypting your password, because you're not going to be sending your password over in plain text. So the client is going to use that salt to encrypt their password and then send it over to the server, and the server will verify the same salt with the same password to check if your login is appropriate. So we've got 8 of those bytes that ends, I believe, right here. Then we've got a filler byte of 00, it's a null byte. You could technically treat this string as a null terminated string with the filler, but the documentation says that this is a terminating filler, so whatever, that's fine. Right after that, we've got capability flags. We've got capability flags in multiple sort of pieces. The lower 2 bytes of the capability flags are right here, and the upper 2 bytes are right here. We'll go into the details of what these capability flags are very shortly. Then we've got the character set and the status flags. So let's take a look at what the capability flags are. The capability flags essentially are a bit mask. So you've got one massive integer that's of 32 bytes. So all the way from byte 0 to byte 31, and each of those bytes represents whether a particular feature is switched on or off for that particular client or for that particular server. So let's take a look at what this really means. If I go into the Handshake documentation and I open the enum that represents capability flags, as you can see, we've got enums representing 1, 2, 4, 8, 16. These are all 2 to the power, like these are all like powers of 2, right? So an example that we can use right now would be the client SSL 2048, or let's, for an easier experience, let's take a look at the client plugin auth. So this says the 19th bit represents the client plugin auth feature. What that means is if the 19th bit of your capability flags is 1, then plugin auth is supported. Plugin auth is supported. Whoa, okay, let's just, otherwise no plugin auth. So if it's 0, then means plugin auth is not supported, and this will come up very often. So for example, right here, we perform an AND operation between the capabilities and the client plugin auth enum. So that essentially lets us know whether this client has allowed, whether the server has allowed or has enabled plugin authentication. And depending on that, you'll get either a 1 byte value or a 0 byte value, or you'll get a constant of zeros. Right after that, we've got a string of 10 zeros, 10 null bytes. So let's take a look at all of that. Oh, right here. Cool. So we've got this is the end of our auth plugin data string. Right after that, we have a filler of 00. Right after that, we've got 2 bytes of capabilities flag. So that's 2 bytes right there. Then we've got 1 byte that represents the character set that we're using. We've got 2 bytes that represent the status flags of the server. So this is what state the server is and whether it's in a transaction, or there are a bunch of states like that. So that signifies the status. That is also an enum similar to the capabilities flags enum. Right after that, we've got another 2 bytes of the capabilities flags. So there, and then we're either going to go into this field or we're going to go into this field. For this particular connection, I've processed the output of this particular if statement, and that brings us into the first branch, and that gives us the auth plugin data length of 15. Right after that, it says there's a reserved string of 10 bytes, and you can see over here there's 10 of these 00 bytes. Now, these bytes are reserved for future use, but if you're developing something like a proxy, or if you're in general, if you're developing a client, this is a very good place to stop and check if you've still got your bearings, because at this point you expect 10 characters, 10 bytes representing zeros, and you should probably in your code verify whether you've got 10 of these bytes, because if you don't, then either your the documentation or the documentation that you referred to build this application has gone out of date, or it could mean that somewhere along the lines you've decoded some field incorrectly, which is causing your offset to go out of whack, which ends up in you not landing right here at the beginning of the 00, zeros, like at the beginning of the 10 reserved zeros. Right after that, we've got a variable length string, and it describes what kind of length it's going to have. So it's either a 13 or it's max of a 13 or the length of the auth plugin data minus 8. It's a little complicated. I don't really know why exactly this logic had to be put in place, but it's just one of the quirks, I guess. Finally, if the server supports some sort of an authentication plugin, or the server recommends some sort of an authentication plugin to actually perform this connection, it's going to let you know through the last field, which we can see over here, says caching SHA-2 password, and it's a null terminated string. So we've got the null byte at the end over here. Great. So this is the handshake. What happens after the handshake? It says on the documentation here that if the client supports SSL, the capability flag is on and the MySQL SSL mode of the client is not SSL mode disabled, a short package called the protocol SSL request is sent, causing the server to establish an SSL layer and wait for the next package from the client. Let's take a look at that. So if we go back to our logs from the connection, you can see that there's some sort of a packet that has some sort of data. And this data again represents the SSL request. So let's take a look at that. Awesome. The SSL request. Great. So like the SSL request packet says, if we are on client protocol 41, so client protocol 41 refers to the protocol that has been active since MySQL 4.1. For all intents and purposes, we're going to be ignoring the older protocols, because if we start considering those, this video will essentially end up being days long. Anywho, so it's a short packet. It contains the capabilities flag of the client. So these are all of the capabilities that the client supports. It's going to have the maximum packet size that the client supports. It's going to have a character set, and it's going to have a filler. So if we look into the packet that we've received from the client, we've got, let's see. Okay, one more interesting fact to notice over here is that our sequence counter just went up to 1. The previous one was 0, 0. This has gone up to 0, 1 at this point. Anywho, right after that, we've got 4 bytes of client flag. So we've got 1, 2, 3, and 4 right here. Then we've got the max packet size, 1, 2, 3, and 4 right here. Then we've got the character set, which is this one right here. And then we've got 23 bytes of filler. So there's 3 right here, there's 16 over here, and there's 4 more here. So there's 23 bytes of filler. Right after that, we can see the logs. It says that the server initiated a TLS connection and the client has also performed TLS. And our TLS connection is successful. So at this point, the client is going to send a handshake response packet. Let's take a look at what the handshake response packet contains. Right after the initial handshake, we've got the handshake response. So the handshake response contains, again, we've got the client flag again. It's 2 bytes. So it's fairly shorter than the server flag, because that was 4 bytes, but either way. So we've got 2 bytes that have the client. Oh, actually, my bad. It's actually just the lower 16 bits of the client flag. Okay, sorry, 4 bytes. I was looking at the wrong protocol version. So this is the old handshake response. This is the new one that has been active since MySQL 4.1. Anywho, so we've got 4 bytes of the client flag, which is always set. where this particular enum is always set. So this particular enum is, I believe, represents 512. So the bit at the position for the 512th for 512 is going to be 1. Then you've got the maximum packet size again. So this part is the same as what we had received in the SSL response, SSL request. After that is where the good stuff happens. So we've got the username. This is where the client actually conveys to the server that, you know what, I'm going to connect with so and so user. It's a null terminated string right here. So I'm connecting using root. So we've got the null terminated string. Then we've got some of the plugin data. All of these are branched instructions. So whether it comes in or not uh, depends on all of your features, all of the features that are enabled and things like that. Then you've got your auth response length, and you've got your optional parameters. So this is a particularly interesting parameter. This is basically a parameter where you can initialize your database at the beginning of the connection. So to give you an example, if I was to connect, this is the old MySQL handshake, right? I'll give an example a little later on down the road. There's a couple things I want to mention before that. Anywho, so if we were connecting with the database at the beginning of the connection itself, this would have held certain values. Right after that, we've got the client plugin name. So MySQL supports several plugins. For example, you've got MySQL native authentication, you've got the caching password, and you've got you've got the normal SHA-2 password, and then you've got the caching SHA-2 password. So all of these various plugin authentication methods, it depends what kind of authentication is requested by the client and what kind of authentication method the server requires. Right after that, we have the connection attributes. So connection attributes, for example, from this packet usually hold data about the person that is connecting. So for example, you've got a PID value, that is the process ID of my MySQL connection. You've got the platform, that is the platform that I'm running. So I'm running x86-64. You've got the operating system, which is Linux. You've got the client name, which is my libmysql in this case. My user, the user that's actually connecting. Then you've got the client version. So my MySQL client's version is 8.0.41. And finally, you've got the program name. Right. So once this is done, we receive an auth switch request. So essentially what has happened is it can either be an auth switch request or an auth more data. So the way the authentication works, if you look into the documentation for the authentication methods, let's actually go here. Authentication phase, fast path. Right. So if you have an authentication method mismatch, so the client tries to connect with an authentication method that the server either does not support or the server requires some other method. So the server is going to going to convey to the client that, you know what, you're going to have to change your authentication method. Otherwise, this can't go further. So the server is going to going to send authentication switch request. This the switch request has the plugin name. So okay, fine. So the client tried to connect using the MySQL native password, but the server expects a caching SHA-2 password. So the server is going to tell the client that you have to use the caching SHA-2 password to connect. And if the client does not support that particular plugin, then the client is going to convey that in the handshake response, and eventually the server is going to return an error and the server is going to terminate the connection. Anywho, so after all of that, once all of this back and forth happens and your connection is finally established, you are going to get an OK packet. So this is what an OK packet is. We'll take a look at how you can decode all of these OK packets in a little bit. But essentially, at this point, we've entered the command phase. So any query, you can perform any query at this point. The client can perform any query. But before that, let's take a look at what happens if we with the database. So right now, if I try to, for example, do show tables, I don't have a database selected, right? I can exit out of here and I can connect with a database. So let's say I'm going to connect to the MySQL database. So that's a database that's always defined. It's a default schema. So you know what, actually, there's a couple things that I will do before that. Let's clear the logs and let's do this. Let's add -a. So I've performed the connection, and now let's take a look at how it works right here. So in the handshake response, as you can see over here, right after the authentication data, my client has conveyed that I conveyed the database name as well that the client wants to connect to. So in the earlier fields, when the handshake response was being sent, the client would have indicated that that it wants to connect with the database, and then finally it gives the it sends the null terminated string of MySQL when it wants to perform the connection. Now that we're done with the connection, let's look at the command phase a little bit. In the command phase, you've got, in broad strokes, you've got two different types of commands. One is your insert kind of commands where you insert data, or you've got your updates where you update data, or the deletes, obviously. And on the other hand, you've got selects. We'll take a look at what the difference between all of these is. So first, let's real quickly, we're going to come up with a quick schema. How about we just ask ChatGPT for this? Generate a quick MySQL schema for this. Okay, that might not be concise enough. Generate a small MySQL schema for me to store user data. Okay, so I think this should work. Yeah, beautiful. We're going to get rid of let's get rid of the email. I don't think we need the email field here. Let's get rid of email. I think the full name, let's get rid of the password as well. Username not null, unique. Yeah, I think this is good enough. Cool. So let's create the schema. Awesome. Now we can go do show tables. Actually, this was a bad idea. I should not have created it in the MySQL. Okay, let's just do a create database shop. Let's call it shop. Use shop. And let's paste this here. Beautiful. So now we've got show tables. Great. We've got a table called users in a database called shop, and we've got our connection over here. So let's disconnect again, and let's, okay, my bad. Now we've entered the command phase. So we've got let's open up the command documentation here. In the connection lifecycle command phase text protocol, let's go to the utility first and the initdb. Okay, cool. So how does this work? Okay, connected, all good. We've been through this, right? Let's delete all of this. Actually, let me connect with the tag here. Okay, so let's delete all of the old logs and let's use our shop database. As soon as I do that, some stuff happens. So it selects the client in the background runs a couple queries. So it selects the current database, then it's going to get an okay and all. We're going to go over all of this very shortly. What's important for us is this packet right here. So this is the packet where the client essentially switches the database. As you can see, the COM code suggests COM initdb. So we've got our packet here. We've got the size of the packet. We've got the sequence, which is 0, 0 again, because once in the command phase, every command will be a 0 sequenced packet. And then we've got the name of the actual database that the user wants to connect to. So let's take a quick look at the COM initdb packet. This is COM query. Let's go into COM initdb. So in all of your command packets, what matters is the first byte. The first byte is going to convey which kind of a command it is. For example, this is a COM initdb command, right? For a query, you'll have a starting byte of, let's open the COM query packet. For a query, you'll have a starting byte of 03. For an initdb, we've got a starting byte of 02. This is actually documented better on the O'Reilly website, where you can see the numeric values for each of these. So you've got the one for sleep, you've got one for quit, initdb, all of this. Anyways, so how does this work? So we've got our let's close this. This is very straightforward. So we've got a COM initdb and it initializes that database. Let's take a look at an insert. So let me do a quick show create table users. Let's do a quick write and insert query for this table. Let's see what it comes up with. Beautiful, this works. So let's run this query. I'm going to clear the logs once again, and we're going to run the query. Great. So it says insert into users with the values Daniyaal_Khan and Daniyaal Khan. Beautiful. So we've got our query here. Again, it's 56. That means it's 86 bytes long. It's the sequence is 00. The COM code is 03, which means it's a query. And then you've got a couple flags, but then finally we start with our query that says insert into users, so and so, the whole shebang. Right after that, we get an OK packet. This is called an OK packet. OK packets are represented by them having either a 00 or an FE at the beginning, which means it's an OK packet. And you've got certain details after that. So let's debug an OK packet. Not exactly debug, but let's look into how an OK packet works. MySQL packets, I think it's in the generic response packet. Yes. So this is an OK packet. It either starts with an OXOO or an OXFE as the first byte of the packet. So this is after the header. This is after the size and the sequence. This is in the payload itself. The first byte in the payload is an OXOO or an OXFE. It's going to have the number of affected rows and the last inserted ID. These are very important. So let's take a look at what we got over here in the response. Right after our sequence number of 1, we've got 00, which signifies that it's an OK packet. We've got 01 and 01, which basically means that the last inserted ID is 01 and the number of affected rows is 01. Then we've got all of this data. Let's insert another user so it is better illustrated. I believe the username is unique, so I'm going to get rid of the underscore here. And we've got one more packet. We've got one more row added, right? And let's take a look at the response for this one. We've got the same sequence of 01. We've got a 00 in the beginning, which is the OK packet header. Then we've got 01, which is the number of rows that were affected. Then we've got 02, which is the ID of the last row that was inserted. Then we've got a couple flags over here. Again, it's the service status and all of that. The service status on all of these flags come into play when we're performing something like, let's say if I was to perform a query, auto commit equals off. Let's say if I was to perform a query like this. that's when the OK packet would return a difference in in the flags, in the later flags. So for example, in this one we had an OK with a 0 1 0 2 0 2 and then three of these, whereas over here we've got a slightly different response. So this signifies the state in which the server is in right now, because the auto commit is now switched off and things like that. So it can suggest that my transaction, for example, if you start a transaction, it will signify that the transaction is started. Let's bring this back to on. Finally, how about I change all of the fields? So if I do update users, set name equals, let's just get rid of my surname. Full name, I believe. Yes, full name. Great. So it has two rows and it changed both of them. And again, in your packet, you're going to get that data. Right here, it suggests that two rows have been modified. So you, as a client, you are now aware how many rows the last action modified, without actually having to perform another query to find out and verify yourself. And finally, towards the end, we have some human readable string that represents the state that the server is in right now. So it's described over here, string EOF. So this is an EOF string, which basically means that at the point from which it starts, you just keep reading until you reach the end of the packet. And on the flip side, since the previous query that I had executed was actually an incorrect query, right? So let's take a look at the OK packet for that. This is the query that I had made, update user set name equals Daniyaal. And since name is not a column that exists, it's full name in this schema, we get this. So we get an error packet. An error packet is nothing but a packet where a response packet from the server right after a query, where the first byte is an FF. The hex representation of your first byte is going to be an FF, which signifies that, you know what, something has gone wrong. You might want to take a look. Real quick, let's go over the error packet. So we've got the error code right after the header. So it's a 2-byte error code. Let's take a look at that. So it's 1E04. Now, like we had discussed about the endianness of MySQL, what this represents is 041E. And if we take a look at the error that we had received over here, it's 041E. So it essentially conveys, this is exactly where the error sort of error code, where the client gets the error code from. So the server has returned 041E as the error code, and you get that on over on your end right here. Now let's take a look at, give me 1 second right here. Right. Okay, so let's take a look at how selects work. Selects are a little more complicated, particularly because they have so much data that they need to send. So let's take a look at how they work. I'm going to do a select star from users. And if you take a look at the logs, we've got a lot of logs here. Right after the query, we've got a bunch of logs. So what does this signify? Let's go over the documentation once again. In the documentation, if I go into the command phase text protocol com query and the text result set. So this is what a text result set is. Now, up until now, all of the commands that we've been performing have been a very request response kind of commands, right? You send one packet as a request and you get one packet as a response. However, result set is one of those places where you send one packet as a request, which is your query, and you're going to get multiple packets back as a part of your response. So this is the result set. It's like a superstructure that is comprised of a lot of other smaller packets. So again, if this flag is true, depends on your on the state of your connection. Most of the time, as if you're using a MySQL client that is on your console, it's going to be false. So how it starts is you get a column count, you get one packet that conveys to you that, you know what, I'm going to send you metadata of X amount of columns, then you'll get that many column definitions. So a column definition is a single packet that represents that represents all of the parts of the column that we're talking about. Right after the column definitions, you're going to receive each of your rows as a single packet. And then after that, you're going to receive an EOF packet or an OK packet. For the most part, it's the same thing. Let's take a look at what this really means. So we perform this query, and in our logs, let's bring this up a little bit. In our logs, it clearly says we've got, this is the packet that we were mentioning right here, int lenenc, which is the column count packet, and we've got a 4 in that, right? So we've got, this is our query was the sequence 0, the response, the column count packet is sequence 1, which says to us that, you know what, I'm going to give you 4 different columns. Then we've got 4 packets that represent the column itself. So what all does this represent? Let's take a quick look at that. We've got the first field, which is always a DEF. These are all string length encoded strings. We've got the schema name, the virtual table name, the physical table name, the virtual column name, the physical column name, and so on and so forth. Then finally, we've got this filler, which is OXOC. Again, this is one of those places where you can perform an assertion to make sure that it's an OXOC, so that you can be sure that, you know what, none of my bearings are off. We're processing all of the data properly. Then we've got details regarding that column, things like the character set. We've got the column length. We've got the type of the column that it is. We've got the flags. Again, these are column definition flags. So for example, if it's not null, if it's unsigned, it's an enum again, and it represents all of these things of the column. And finally, you've got the decimal. So in MySQL, you've got this ability where you can decide how many digits you are reserving for the decimal versus how many digits you want for your mantissa. So all of that is represented in a single response that comes at the start of the query, at the start of the response. You get all of those definitions. So as we can see, the virtual table name is shop. The schema name is shop. The virtual table name is users. The physical table name is also users. Column, again, virtual column name is ID. Physical column name is ID. And then you've got all of those flags right here. So once we've got 4 of these columns, the number that was conveyed to us in the beginning, once we've got that many columns, we can start processing the remaining packets as rows. And these are all of the rows. So we've got 2 of the rows, and these rows are all string encoded in the format of the columns, in the order of the columns. So for example, right here, the first column that we had received was the ID column, right? So in our row, the first field that we get will be representing the ID. So as you can see, this right here is what represents the ID. Then the next column that we received was the username. So the next field over here is going to be the username. So it's a 0D here. So that essentially means it's 13 characters long, which is my name right here, along with the underscore and the surname. So right after 13 characters, we get the next field, which is the earlier one was the username, then it's the name, then finally we've got the I believe username, full name, and then at the end we've got the time that which this row was created. Then towards the end, once this entire result set wraps up, once the server is done with all of this, it sends an FE packet that signifies that, you know what, I'm done with sending all of this data. And that's the end of the result set. And then now we're in that state again where the client can perform commands again. And that pretty much brings us to the end of this video scope. If you're interested in further explorations, there's stuff like the com statement prepare, com statement execute. That's the binary protocol. If you're interested in that, feel free to leave a comment down below. I'll create a video on that as well. But it's an incremental step from the topics that we've covered in this video. Apart from that, there is a protocol called the MySQL replication protocol as well. That is very interesting. And that's what happens. That's what comes into use when, for example, you're performing a MySQL master slave setup or a master master setup. So it's very it's an interesting um, uh, rabbit hole to look into. Anywho, that brings us to the end of this video. I hope you've enjoyed it. It's good to be back making videos. And if you have any topics that you would like to cover in any of the future videos, feel free to leave them down in the comments below, and I'd love to take them up. Thanks for watching. Bye bye.